So, do you guys know how to turn off the battery saving thing on the iPad? Settings.
I can help you for extra credit.
For extra credit, you'll help me. All right, good. Thank you. That should have been easier than that, but I'm sorry. Okay. Well, last time as we were finishing up, we made a big deal out of the fact that unlike a typical beta keto acid that we see, where decarboxylation has a great leaving group attached to it, or in other words, a decent leaving group. So here's a beta keto acid. There's the carbonyl carbon. There's the alpha carbon, there's the beta carbon. And we talked about how the stuff in green can be kicked off by as a leaving group by the pink oxygen, because the thing that leaves is a resonance stabilized enolate, in which the lone pairs from the bond between the carbonyl carbon and the alpha carbon, the bond that breaks, those lone pairs end up on the enolate, which is stabilized by resonance, and we can draw a resonance structure that looks like this. Okay? But we commented on how for an alpha keto acid, when the bond between the alpha carbon, if we were to try to do a decarboxylation, when the bond between the alpha carbon and the carbonyl carbon breaks with the kicker-offer group kicking down, those electrons don't have anywhere to go that would be stabilized by resonance. In other words, what you would get is this weird leaving group with an sp2 carbon and a lone pair in an sp2 orbital not stabilized by resonance at all. And in fact, that's the conjugate base of an aldehyde. And I said that the aldehyde's pKa is really high. It should be probably in the 40s. So this is not a leaving group. So the problem with the alpha keto acid is that we don't have a good leaving group here, which is why I'll temporarily highlight it in gray. So we can't do traditional decarboxylation, and that's why this reaction is so difficult and why you need these complicated cofactors. All right, are there questions about that setup? Remember our discussion there? So, what we're actually going to do instead is we're going to use the cofactor thiamine pyrophosphate, or TPP for pyrophosphate for short, and it's the negatively charged carbon that acts as a nucleophile. So the nucleophile it's both a nucleophile and a leaving group, so maybe I should highlight it in purple and in green, I don't know. The nucleophile attacks the carbonyl carbon, the pi bond breaks, the carbon-oxygen pi bond breaks and picks up a proton from the acid, and we get to this intermediate. And the thing that I wanted you to notice about this intermediate is the presence of the TPP group makes it so if the bond between the carbonyl carbon and the alpha carbon broke as the result of the pink oxygen acting as a kicker offer like this, the electrons from that bond would go on the alpha carbon, where they're going to be adjacent to this key pi bond in the TPP group. So here is the structure of what we've got, and we'll call the carboxylate carbon the blue carbon. So here's our CO2, the blue carbon that used to be the carboxylate group, the pink oxygen that was the kicker offer. The lone pair in the structure up top is on what used to be the alpha carbon. And notice that that lone pair is adjacent to a pi bond where it can be stabilized by resonance. So I can interchange the resonance structure on the top with the one on the bottom, where now I have a pi bond between the alpha and the beta carbons, and the lone pair is now on the nitrogen. So the point is that TPP enables a resonance stabilized leaving group. And therefore decarboxylation can happen. Okay, now all of this, because of the influence of TPP, all of this is now a leaving group. All right, so we're using TPP to temporarily get ourselves into a situation that's not so unlike a beta keto carboxylate that we saw before. And this is how nature decarboxylates alpha keto acids. All right, so that's key. That's a really important thing. What questions do you have about it? Shoot, you guys are quiet today. You're tired. Go ahead.
There be questions about reversibility.
Is there questions about reversibility here? Well, the decarboxylation, anytime you see a decarboxylation that's in humans, in human biology, that's not reversible. It would be lovely if you could breathe in CO2 and have it added to a molecule and have it stay and then use it. That's called carbon fixation. There is an enzyme that does that. It's in plants, and that's part of how plants make their own glucose. Yeah. Yes.
Our problem set asks us to use energy levels.
Yeah.
Explain why things aren't reversible. Could you do that with this?
So could you do that for this reaction? Does your problem set ask you to do this on this reaction? I didn't think so. Okay. Well, so energy levels would be a little bit challenging here in the sense that I'm not sure what to do with CO2.
Okay.
CO2 is not a great electrophile. On the other hand, if I compare where I start with a ketone and where I end up, which is a thioester, that's about the same level. So yeah, I'm not totally sure what to make of that. It's a good question. I would say if you were just comparing the levels overall, you'd be like, oh, ketone to thioester, no big deal, reversible, neutral, except for the loss of CO2. So once you lose CO2, you're committed. There's no going back. And that may not be an issue so much of energy levels as it is of entropy and the fact that once CO2 is gone, it's a gas and it's just gone. Yeah. Okay, good. Others? All right, so that was the decarboxylation step. And this reaction sort of proceeds in three phases. The first is decarboxylation. The second phase is oxidation. So phase 2 is oxidation to a thioester. Because if you're sort of paying attention to what's gone on here, you've got a carbon in this resonance stabilized intermediate, and I'm now going to erase these arrows because I'm going to need to do something different. You got an intermediate where a carbon is negatively charged, and if you picked up a proton on that carbon, and then if you kicked off this leaving group, you'd have an aldehyde. But what we want is a thioester. So what ends up happening is the lipoamide cofactor in the enzyme active site is held really close to this negatively charged alpha carbon. And the other thing that I think I mentioned last time was that sulfur sigma bonds are weak, and therefore that the sigma star, the antibonding orbital associated with the sulfur-sulfur bond, is low in energy, meaning it's the LUMO. So you've got a nucleophile here in this step attacking a sulfur sigma star, and the effect of that should be to break the sulfur-sulfur bond. This is a direct substitution type reaction, okay? So if we're summarizing what we've seen before, in the decarboxylation reaction, we first saw an addition step to a carbonyl, and then the decarboxylation step is really an elimination step of a leaving group. Here is that leaving group. It happens to have a negative charge on this carbon, where that lone pair is somewhat shared with this nitrogen. The negatively charged carbon acts as a nucleophile and attacks the sulfur sigma star. What would that look like? Well, you'll attack one of the sulfurs. The enzyme controls which. There's no reason you'd be able to predict that one way or another. But the enzyme controls attack of the sulfur sigma star. And we break the sulfur bond, and the resulting negatively charged sulfur, we could draw the mechanism this way and then show a negatively charged sulfur picking up a proton in a subsequent step. Instead, to save time, we'll combine this with the proton transfer step where that negatively charged sulfur picks up a proton. So this is kind of a direct substitution step, and it works because the two sulfurs are, the sulfur bond is weak. All right? Okay, questions about that? Now, here's the trick. If you look at the product of that reaction, this carbon has one more bond to a heteroatom than it used to. So the carbon that used to be negatively charged, we're going to now say is oxidized, whereas the sulfur used to have, the lipoamide used to have a sulfur-sulfur bond. Now it has a sulfur carbon and a sulfur hydrogen bond. So the sulfur-sulfur bond got reduced. Okay. So you could think of this lipoamide disulfide functional group as an oxidizing agent, because it oxidizes the alpha carbon. And the reduced form of a disulfide is a molecule that has just two sulfurs attached. This is a dithiol. So we've reduced the disulfide to a dithiol sort of oxidation state. Okay, so that's why I called this second phase oxidation. And you'll see that it's oxidation because as we go to the next step, we're going to treat TPP like a leaving group again. We're going to have the conjugate base of our acid deprotonate the OH. This is going to be a carbonyl oxygen. This will be the carbonyl carbon. We'll deprotonate the OH. Electrons will kick down and then kick off the TPP leaving group. And these are the products. TPP as the leaving group here. Here's carbonyl carbon, carbonyl oxygen, and now one of the sulfurs that used to be in lipoamide is involved in a thioester. Okay, that's kind of a lot. What questions do you have about those steps that we just talked about? I can't tell if it just all makes sense or whether you're so overwhelmed that you don't even want to say anything. I'm guessing it's part 2, but it might be part 1. Go ahead.
I was just gonna ask if the lipoamide disulfide, if that R wedge turns into the dash on the
Yeah, it does. It's not a switch in stereochemistry, it's just a switch in perspective. We can verify that real quickly. This would be priority 1, 2, and 3. So the stereo center there is R, appropriately, I guess. And it should be that way here. Proton is up, 1, 2, 3. Looks like counterclockwise, but since proton is up, it's still R. Yeah, so we've just extended the chain and are unfolded it and looking around at it from the other side. Yeah, go ahead.
I'm just wondering, in the product, where the sulfur coatings at came from?
Right, this is now a starting material for the next step in the reaction.
So
That didn't come from the elimination step. Yeah, lipoamide is actually connected to the protein, so we need actually something to come along and liberate our acetyl group from the protein, so it can be transported to the citric acid cycle. So we bring in another thiol and swap out thiols. What else? I mean, come on, if you're overwhelmed, go ahead. Somebody's got it. Yes?
So when we're studying the whole glycolysis, is it more important for us to be studying the mechanisms, drawing the arrows, or is it more important to understand why the arrow is being drawn, why it's attacking that one? Sorry, not another one.
Is it more important to be able to draw the arrows or understand why? I think it's more important to understand why, because if you know that, then you can draw sensible arrows without just having to memorize them. You are right that it would be harder if I gave you nothing other than what's up here and I said draw the mechanism. I feel like that's kind of that's more of a difficult problem. If instead I show you a bunch of intermediates and then say, like I've done here, you push the arrows, then if you have some experience with HOMO, LUMO, and you look at what's changing, you can probably work your way through. I think that's more what I'm looking for. What else? Yeah.
How many intermediate steps would you skip for us? Like how hard would the problem get?
How hard would the problem get? Well, there are multiple ways to do a mechanism question. I could say, what's the structure of the missing intermediate, and show a whole mechanism, but one intermediate's missing. I could, as I've said last time, which arrows are wrong versus which arrows are right. Sometimes I'll show starting material and product. As I think I said last time, I'll show in options A through whatever the various mechanistic steps, and some of them will lead to the product and others will look funny or look reasonable but be wrong. And so, yeah, you have to know enough about it that you can identify a good mechanism from one that's wrong. Yeah.
Can you just quickly go over the difference between glucose versus fructose?
Okay, yes, but tell me where that's coming from.
I'm just looking at the quiz, and
Oh, you're already skipping ahead?
just to like see how fast the memory is.
Yep.
Anyway.
We are going to do that, and we'll go through that. What I'm going to do is, once we finish with this pyruvate dehydrogenase complex, then I'm going to show you two other ways aside from mechanism that I can ask you questions about glycolysis and other things.
And it's just the base of the molecule is the same besides
Yeah, we'll talk about that. Can I punt on that for a few minutes? Okay. Others? Okay, well, so the last couple of steps are that, as I said, the lipoamide group is attached to the enzyme. So we've succeeded in oxidizing what used to be a ketone carbon to a thioester. And that's great, but it's currently attached to the enzyme, so we have to liberate it. What we're going to do here is called thioester exchange. All that means is we're going to do an addition and then elimination step to release the thiol from lipoamide and incorporate the thiol from coenzyme A. So base removes a proton from coenzyme A. The resulting negatively charged sulfur attacks the carbonyl carbon. You break the pi bond, electrons go up onto the oxygen. You get a tetrahedral intermediate. That's an addition step. Then electrons kick down and the thiol from lipoamide leaves as a negatively charged sulfur, and on its way out, it picks up a proton from the conjugate acid of the base. So that gets rid of the lipoamide thiol, and our acetyl group with our carbonyl carbon and carbonyl oxygen is now attached to the coenzyme A nucleophile, and that goes off to the citric acid cycle, where it's oxidized further to finally release 2 molecules of CO2. Now, enzymes need to, in order for enzymes to be useful, we have to complete the circuit. That is, they have to leave everything, they have to be prepared for another round. And lipoamide, which is still attached to the enzyme via this R group, is now the dithiol, and this is the reduced form. But notice, in order to catalyze a new reaction, that dithiol is gonna need to be the disulfide. So the final step is an oxidation step. And I'm not gonna, the chemistry here is complicated. It's not as easy as you might think. Effectively, if you wanted to think about it, you would have a base remove a proton from one of these sulfurs, and then the resulting negatively charged sulfur would attack the other sulfur, and a hydride would be delivered to NAD+. Now that's not actually what happens, it's more complicated than that. But you're using NAD+ as an oxidizing agent. The dithiol gets oxidized to the disulfide, and NAD+ gets reduced to NADH. That regenerates lipoamide, and now we're good to go for a whole other cycle. So let's see, overall, what steps? Decarboxylation, oxidation to the thioester, 3, thioester exchange, and 4, oxidation, reoxidation of lipoamide. All of this takes place in a 3-enzyme complex called the pyruvate dehydrogenase complex. 3 different subunits, some of them catalyze multiple steps, and all of this is required before you can get to acetyl-CoA. And of course, remember that glycolysis gives us 2 pyruvates for every molecule of glucose. So we're going to get 2 acetyl-CoAs, 2 CO2s, and 2 NADHs out of this. Yeah?
So I know
Okay. I mean, yeah, the actual enzyme mechanism, I thought I knew how this step worked, and then I looked up the actual enzyme mechanism and was like, whoa, okay, that's more complicated than I wanted it to be. So I will show you something, but I have to tell you what I'm going to show you is wrong. It's like not true. Conceptually, it'll give you an idea of what would need to happen, but actually the way nature does it is more complicated. So I'm not even going to Obi-Wan and say that what I'm telling you is true from a certain point of view. This is definitely not true. But I can give you an idea of how a hypothesis that turns out to be wrong, but at least shows you where a hydride would go. So a base from the enzyme would remove a proton from one of the sulfurs. Then the resulting negatively charged sulfur would attack the sulfur hydrogen sigma star from the other sulfur. That would create a new sulfur-sulfur sigma bond, and hydride would leave but be delivered directly to NADH to give you that. That's, and I'm going to erase that because that's definitely not what happens. But that shows you how when you make a disulfide, you got to lose a proton and a hydride.
And so what makes the dash wedge? Just like out of curiosity.
Just perspective. It's literally a pancake flip of the molecule. And you can convince yourself, just assign the stereochemical configuration for that carbon there and that carbon there. It's the same thing, it's just a different view. Yeah?
Is that something we're gonna have to like memorize to know how to do, or just?
This?
Yeah.
No, because that's not actually how it happens.
So this step we don't really.
This step you don't need to know the mechanism of. So I'm going to erase the hypothesis that gives you at least an idea that the disulfide, that the dithiol has to lose a proton and a hydride. And we'll just delete that. And we will write here in blood, I promise not to ask about the mechanism of this particular step. Of this particular step. I have to be very legalistic about this because it's in blood and you're going to hold me to it. In perpetuity, all my love. JLP, drip, 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 drip. Okay. Kind of grisly. Okay. If you need a spit handshake, I'm just kidding. Okay. So overall, look at what happens. And we're going to need to add this to our tally. On our glycolysis handout, where was that? Well, that would probably just be last time. In our glycolysis handout, I showed you that glucose going through glycolysis to pyruvate generates 2 ATPs and 2 NADHs. Now I've shown you how 2 pyruvates lead to 2 CO2s, 2 NADHs, and 2 acetyl-CoAs. And so now we're fully accounted for the 12 ATPs we get from one glucose up through acetyl-CoA. All right, now you're going to somewhat be blown away because that's only a small part. We'll generate probably 2 times as much that ATP. We'll do the math in the end. But about twice as much ATP from the citric acid cycle than we get from glycolysis. All right. So with that, other questions about the mechanism that we just went through? Okay, now we get to see how well you've been doing at following along. So here is one way that you can ask a question about glycolysis. I could have shown you isolated intermediates, and maybe I should. I'll give you one. I'll give you one isolated intermediate. In this box goes glyceraldehyde 3-phosphate. Now, in this format of a question, I'm showing you all of the cofactors and co-reagents. I'm even giving you enzyme names so you know what has to happen with each step. And if you're smart, you use the test to take the test. For example, what if you didn't know this box had glyceraldehyde 3-phosphate? Well, look at the enzyme that acts on it. That enzyme will either be named for this molecule as a substrate and what the reaction is in this direction, or it might be named for the product as a substrate and what the reaction is in this direction. In this case, glyceraldehyde 3-phosphate is the substrate. So if you didn't know that what the name of this was, you could have figured it out from the enzyme name. And then the other part of the enzyme name tells you what it does. It's a dehydrogenase, which is a clue. Dehydrogenases do oxidation/reduction chemistry. And now you look at the other reagents, NAD+, going to NADH, and you can say, oh, NAD+ is the oxidizing agent, and NADH is the reduced form. So now you have an idea of what goes on in this reaction and can make a prediction. All right? So I know there's a question outstanding about what glucose is and what fructose is. I'm going to still punt on this till after you've worked on this to see how far you can get. Okay? So your quest is to fill in each and every box with the correct structures and the correct names. Try to do it without looking at your notes. You have all the answers. They're on the glycolysis handout, right? I don't want this to be busy work. Can you copy down something from one place to another? I know you can do that. What I want to know is what's in your brain and can you figure stuff out? And so work on that. I'll wander around for questions. You can buy a hint by exchanging your extra credit point for a hint. No, I'm just kidding. I actually had a professor who would do that. It was Dr. Savage when I took OChem from him in 2001. On an exam, we had exams he would schedule outside of class. He'd show up at like 7 o'clock at night and you'd just stay until you were done. And if you got stuck, you could go up to the front and buy a hint from him. So for 5 points, I'll give you this hint, he would say. Some people took him up, some people didn't. So anyway, get to it. I won't make you purchase a hint, but see how far you can get with that one. I guess also understand this is probably harder than the actual test is going to be, or maybe easier. It's hard to tell. You don't have to choose between various options here. On the test, you have various structures that you would put in for the missing boxes. But I'm perfectly capable of putting in things that look a lot like, for example, glucose, but are subtly different. So, kind of got to know your stuff. I revealed my true character to you yesterday with the helmet and the lightsaber. I would ask you to fill in this. sorry, these boxes are small. I forget that I can zoom in and expand them online.
Question.
Yeah.
For glucose, it isn't the first carbon on this matter.
That's right, it doesn't matter whether it's a dash.
So it's good to draw it, what should dash?
Not wrong.
Oh, yeah, okay.
Oh, okay, we have the same stuff going on. I don't know what this is.
Okay, if you're stuck on something and you need a hint, feel free to look at your notes, but don't look at all of your notes, just a hint on that thing, and make a note to yourself that when it came down to it, you couldn't remember what that one is, so that's what you want to review. Okay? Don't just do the thing where you're like, oh, I see it now, I'll remember it. That's wishful thinking, but it is not useful in the testing center.
Like, not just like.
You want to create those molecules.
It's just arguing.
See, that's what I was saying. No, it's a fructose.
Oh, so we start with this, what, how do you use this?
It'll make your life easier.
Just for fun, I'm also going to give you a little hint about the enzyme names that are named for the backwards reaction. So this one, the gray arrow here just simply means the enzyme, or the green arrow means the enzyme is named for the backwards reaction. So it's these two. Yeah.
For the phospho, notes are aldehydes.
Yeah.
Well, we have to go to open chair form. We have open chair on here.
So on the aldehydes, you can continue to draw whatever is supposed to go there. I see what you're trying to do. No, you're free to draw the ones for the open. sense for how things are going. If you got 8 boxes empty, 5, 4, 3, 7 still empty, 5, 3 still empty. You want to see the mechanism for that again? Okay. Yes, hence deprotonation and reprotonation. Copperization and there's ethyl. Decationation. Yes. All right, how are you doing? Okay, let's take a minute to identify the challenging pinch points, as it were, and let this be motivation for sort of what you're going to need to be able to do on an exam. So I think a lot of you were able to say this is glucose. Yep. Could you draw the structure of glucose? Good. All right, I'm not going to bother. Oh, fine. If you insist. Okay, and then hexokinase. Kinase tells you it transfers a gamma phosphate group from ATP. Hexo tells you it does this on a 6-carbon sugar, a hexose. Which of the 6 carbons, which of the hydroxyl groups on glucose gets the phosphate? And if you didn't know that, go to the next enzyme name, which is named for the forward reaction, and you can see that this substrate should be glucose 6-phosphate. So use the test to take the test. If you see the enzyme name, then that can be a hint as to what you're supposed to do and where the phosphate group is supposed to go. So that's glucose 6-phosphate. Okay, the name here tells you it's going to isomerize, and then looking at the name of the next enzyme, there's the word fructo in there. So that's a hint that the next molecule is fructose 6-phosphate. You know there's not an additional phosphate group because this enzyme is not a kinase and there's no use of ATP. So the only thing that's going to change is going from glucose to fructose. Now, as you recall, fructose is a furanose, meaning it has a five-membered ring with oxygen, whereas glucose is a pyranose, meaning it has a 6-membered ring with oxygen. For fructose, the connectivity and the stereochemistry is almost the same as glucose for atoms 6 and 5 and 4 is going to have the same stereochemistry as glucose, and 3 is going to have the same stereochemistry of glucose. Remember, though, that fructose is a ketose, meaning the anomeric carbon is going to be carbon 2, and that's going to have an OH group, and then C1 and the C1 hydroxyl. And we're not going to care too much about the stereochemistry of that anomeric carbon. Okay, remember that fructose is a ketose, glucose is an aldose. In the open chain form of glucose, glucose is an aldehyde. In the open chain form of fructose, fructose is a ketone. Yes?
Two questions. Do we know that the fructose is fructose 6 because of the glucose 6-phosphate?
Yeah, this 6-phosphate group stays exactly the same, no change.
Okay. And then what does kinase mean?
Kinase means transfer of a gamma phosphate, generally from generally kinase reactions do phosphoanhydride in ATP to phosphoester on another molecule. Yeah.
So you're adding phosphate.
Yeah, you're adding a phosphate to glucose.
Okay, and then, so, should we know the mechanisms, like, is it, we're just skipping the intermediate between glucose? and
Right,
glucose?
so this is not a mechanism question, which is why I haven't asked you to show any intermediates. On an exam, you have to have multiple ways of testing things. There's what, there's how, and there's why. What is typically easier to test because you can either fill in the molecule or not. Why is an issue of, is this a level 1 versus a level 2? Are we uphill, downhill? You can do that. How is generally even more complicated because then you get into the details of the arrow pushing. And I've talked a little bit about how I'll ask questions about that. And it is good for you to be thinking, okay, I need to review this mechanism. I can't remember how that works. And that's a indication that there's something that you should review there, though that wasn't the question here. I wasn't asking for the arrows. If you remember, though, we can say it in words. OH on C1 acts as a nucleophile, gets deprotonated, attacks the gamma phosphoryl group on ATP. There's an intermediate. Electrons kick down, ADP is released as the leaving group, and you make the new phosphoester. Yeah?
For the, we haven't done this one yet, but for the phosphoglycerate, so after the phosphoglycerate,
Yeah.
is the reason that it loses the phosphoryl group because it goes from, instead of ATP to ADP, it's ADP to ATP?
Right. Good. So what you're going to see is in this step, we start with 1,3-bisphosphoglycerate, and then we go to just phosphoglycerate. And ADP acts as the nucleophile and removes the 1-phospho group from this starting material. And you end up with ATP. So this is a kinase reaction run in reverse. Yeah. All right, we need a bit of a break. Let's take 5, and then we'll get back at it. On the reverse side of the quiz is a quiz about what the enzyme names are, so you can see what to expect there. Let's keep working on it.